So today we're going to do the second derivative, and all the second derivative is you do the derivative once, and you can't quite get enough of it. So you're like, I'll take another derivative after I do the derivative once. And we're going to find out in our next unit that this has some applications for graphing, and it has some applications for physics, because the derivative, as you go along, derivative of speed, of distance, of displacement, is speed. And then the second derivative becomes your acceleration. So you've got applications in science and stuff like this. And there's a bunch of notations. If you're using the f prime notation, you just add another prime. So you could do the second derivative. If you want to do the third derivative, you could put another prime there. If you want to do the fourth derivative, if you want to do the 500th derivative, you could just develop a tick and just draw it all the way along there, and you'll be fine. Of course, sometimes what they do is if they do too many of them, they might get lazy and just say there's 500 of them there. But we're not going to do the 500th derivative. We're going to focus mainly on the second derivative today. So there's one notation. And of course, if you had the y prime notation, which is very similar to f prime of x, just add another tick mark there. With the dy dx notation, it's a little bit different. Makes sense that you're doing it twice, so the 2 is there. But the first 2 is between the d and the y, and the second 2 is after the dx. And we sort of read that as d2y by dx squared. And that's in Leibniz notation. Part of the reason for this notation that I can think of is when you were doing, let's say I wanted to take the derivative of x squared. In Leibniz notation, sometimes we write this in front. And that means take the derivative of x squared. And this x squared is technically your function y. So what would it look like if I took that derivative twice? Well, I'd have another d dx in front of that. So I have the dx squared. Technically, maybe there should be brackets around the dx. But then mathematicians don't like brackets, so they just say, we'll just accept that. And then I have d and then d again, so that's why it's d squared. And then the y, which is your function, happens at the end. So that might be an explanation for why that notation looks like that. Anyways, you're never going to be tested on why notations look the way they are. So let's get to some questions. Here's a function. Could you take the derivative once? And then if you take the derivative once, could you take the derivative again? Would that be difficult? Sometimes you're going to find that after you do the derivative once, you may want to simplify. You may want to change some things around before you get to that second derivative, because it just makes doing the derivative again easy. In this case, our first derivative is not bad at all. Okay, you would probably take the time to rewrite your negative 5 over x as negative 5x to the minus 1. But maybe now you're already good enough to just think that in your head so that when you get to your derivative, you could go to it directly. So the negative 1 came out in front. That's why we got our plus sign. Subtract 1 from the exponent. That's why we got our minus 2. There's nothing really to simplify here. It is a pretty simple function to begin with. Everything is with polynomials. So you can just use your power rule. And so when you take the second derivative, you just do the rules again. And we could keep on going if we wanted to, take the third derivative, fourth derivative. But it's fairly straightforward. So when looking at this one's not quite as straightforward. X squared minus 3x cubed means that we have a chain rule. And if we're going to find d2y over dx squared, we're going to take our derivative first and see what that looks like, and then take our second derivative. So what does our chain rule look like? Do the derivative outside function. So the 3 comes in front, subtract 1 from the exponent, nothing changes inside. And then you take the derivative of the inside. Here it makes sense to simplify a little bit. Can you see that I multiplied this 3 by the 2x minus 3 just to put things together? Now that we've got our first derivative, what do we notice? We notice we have one function multiplied by another function. So we're going to have to use a product rule. And in that, you see that in the second function, we're still going to have a chain rule. So how does the product rule work? Keep the first one the same. Derivative of the second one, and notice I did the chain rule in the second one here. The number comes out in front. Subtract 1 from the exponent. Then the derivative of the inside. Plus, keep the second one the same, and the derivative of the first one will just be 6. Sometimes with a chain rule, a second derivative can get really complicated really quickly. Another option for this one, if you wanted to expand this, with the binomial theorem, you could. See how I have Pascal's triangle in there? 1, 3, 3, 1 for expanding something to an x cubed. And my powers went x squared 3, x squared squared, x squared, and then none. And the other ones went up by 1. And so if I expanded this completely, I'm going to get x to the 6th minus 9 for x to the 5 plus 27 x to the 4 minus 27 x cubed. So if I took the time to first expand it completely, that took a little work. And depending on what the power is, you may decide that that work isn't worth it. I've expanded functions a lot more than you have, so I'm quicker at this. But even though that I'm quicker at this, I still would have chosen our first method. I still think I would have done the derivative directly to begin with. But anyways, now that we've done it, can you see how easy the derivatives are? Except for the 27 times 4, right? And then when you take the derivative again, they're also easy, except for the big numbers, right? So if we expanded our answer that we got in the green here, it should match with this, barring any mental math errors that I made in the last 10 minutes. So here, I'm going to just let you try these next ones. There's 4 of them there. We'll put up the answers in a second. Some of them will have the chain rule. Some of them will have product rule. Able to see the chain rule in the second one? And then you would have the chain rule in the second one again. And now the derivative of cos is negative sign, so that's why the plus sign appears. In the second one, we've got a chain rule. First the derivative is 1 over, and then you multiply by the derivative of the inside. Then once you've done the chain rule, now we have quotient rule. So keep the bottom one the same, derivative of the top, minus keep the top the same, derivative of the bottom, over the whole bottom squared. So our first derivative has the product rule and the chain rule. Now here it's been factored, but it wouldn't necessarily have to be factored. Just looking at it and said, oh, if I factor it, I still have a product rule. But you would still have the product rule if you didn't factor it, because you'd have a product rule in the first set, but the second one wouldn't. Either way, when you take your second derivative, you will get this. How many people did the second derivative directly from this one? Did anyone do it directly from that? Everybody factored first? Okay. And the last one. First derivative is a chain rule. Second derivative is a chain rule again. First of all, an example 4. The math actually isn't very hard, right? We take our first derivative, negative 32t plus 16, take our second derivative, and we just get negative 32. Now, initially looking at this question, we have a parabola. Some things we know about this parabola is we know that the y-intercept happens at 32. We know that it's a parabola pointing down, like that. So this is an idea of what that graph looks like. Okay? Now, as an application of this, well, the notation here, t looks like time. S is a notation often for displacement. So what is happening here is maybe someone is on a cliff at a certain height and throwing a baseball up into the air. Gravity affects that baseball, it comes back down. Now, as soon as you take the first derivative for any displacement becomes your speed or your velocity. So this, now we've got an equation for how fast this object is moving. What's really cool about that formula is if you take t equals 0, which is time, we know that this object was initially thrown at 16 something per second. I'm not going to talk about units yet because that's going to be important in the end. Now, when we take a derivative of our speed, of our velocity, we get acceleration. What does acceleration do to gravity? Negative 9.8 meters per second squared? Yes? Physics tells you that? Science tells you that? Okay? But we got negative 32. So this, and it's rounded. It's not exactly right, but it's part of, if it was from an American textbook, you'll get negative 32. So a lot of Canadian textbooks, whenever they're doing displacement, will have negative 4.9 or negative 5 if they want to make the question easier as the value in front of t squared. American textbooks will often have 15 or 16. Because if you would convert, if you think about 5 meters, there's about 3 feet in a meter. So it's going to be around 15. There's actually a little bit more than 3 feet in a meter. So it maybe gets close to 16. So that's why we have these numbers. But it's neat because if you double this number, you see your acceleration. And whatever number's in front of t, that's your initial velocity. So there's some really neat things in every parabola that's representing gravity. And of course, the last number is whatever height. So this person was on a cliff 32 feet high when they threw that baseball. This equation's not that exciting for me. Maybe it has some significance in biology that I don't know about, but it doesn't look that exciting, other than the E, because my name starts with E, so that's cool. So we take our first derivative. Again, it has a chain rule. You have to notice that there's a function inside of the function. Simplify it a little bit and do the derivative again, and it has the chain rule again. And then if you wanted to find f double prime at 1, you just plug in 1 to 3 sig figs, you get 118. Trying to think of a 6-7 discriminator question for this. I think on a final exam, if they wanted to create something a little bit different, they would say let fn of x equal the nth derivative. What would it look like to find a formula for fn of x? Do you notice a pattern that's happening? If you did the third derivative, what's going to happen? Everything's going to stay the same, and then when you do the chain rule, it's going to become 32 e to the 2x. So what's happening to our first numbers? They're doubling. And if they're doubling, what unit is that from? Geometric sequences in series. So what they're going to sometimes do on an exam is say, if we ask you a derivative question, I bet you the last thing you're going to be thinking about, especially if we use e, is geometric sequences. You might think of logarithms and exponents because it's got e in it. You're going to think about derivatives, but I don't think you're going to think about geometric sequences. So let's put that into a question with e to the x and see if you're able to take a step back, look at that pattern, and say, well, if I'm going 8, 16, 32, 64, how do I write a formula for that? Well, my formula, term 1 is 8. My common ratio is 2. So if I wanted to find term 2, I'd use that formula. So now my nth derivative, fn of x, will equal now we've got a formula for the number in front, and the e to the 2x would stay the same.